Okay. At the rank 2, we have team 14 sinusoidal dial. The final performance is like 0.42, so it's like 0.02 improvement compared to the rank 3 teams. And we're gonna listen to their videos.
Hi everyone, we're Team 14, also known as Sinusoidal. My name is Leo Dupire.
And my name is Dhruv Shetty. We are going to be covering our model WNet. So the problem we were tasked with was to generate the semantic segmentation mask of the 22nd frame given 11 frames. The frames showed objects of varying materials and colors moving around and colliding. Using only 11 frames, the model must predict what position the objects will be in on the 22nd frame, approximating the underlying physics such as velocity or the material of each object. So we tried 4 different approaches initially. We experimented with pretext tasks like predicting object attributes and the relative positions. We attempted to use a transformer-based autoencoder to learn object representations. The encoder part captured the representations, while the decoder part reconstructs the 22nd frame segmentation mask. The purpose of the transformer was to use attention to deal with the temporal aspect of the data. We also tried using momentum contrast, which is a self-supervised learning method that uses a contrastive loss method to encourage the model to learn similar representations for positive pairs, such as augmentations of the same video, and different representations for negative pairs. We attempted to train on the large unlabeled dataset, which could then be used for predicting object positions. We finally settled on UNet. UNet is a widely used architecture for semantic segmentation tasks, featuring an encoder-decoder structure with skip connections that enable precise localization. We decided to use UNet for our final implementation due to its proven success in semantic segmentation tasks and its ability to generate high-resolution masks. Finally, we came up with WNet, which is a combination of 2 UNet models, a masker and a predictor, working sequentially to predict the 22nd frame mask.
All right, so here you can see quite clearly why WNet is called WNet, because we have the 2 units, the masker feeding into the predictor. Now the architectures between the 2 are quite similar. We've got 31 million parameters for each model, but the main difference comes from the fact that the predictor is being looped 11 times, therefore predicting the next image 11 times until reaching the 22nd image. And this is because we actually trained the predictor to predict the next image rather than just the 22nd image directly. And so we found quite a few benefits from this. And so the theory is that if we can predict the next image very well, then the generated image of the generated 22nd mask will be very accurate as well. Now the positives are that it's much easier to have a model that has a fixed input size. And so we can keep this model with just kind of like a sliding input or the sliding window of 11 masks coming in and out. And we keep on feeding in the last generated image into that sliding window. And however, on the other end, we've got negatives, which are, any flaws in the model will become very apparent very quickly, once you go pretty deep into these predictions. And so we also had some ideas on how to address this, but I'll be covering that a little later. Now our results, so now using the masker and the predictor models in our combined WNet, we ended up getting a Jacquard index score on our validation set of 0.4212, which was quite decent compared to or a decent improvement compared to our practice of 0.28. And now for future steps, we've got a few ideas on how to improve the model. So the first one would just be increasing model size. But we also want to look into some self-supervised learning techniques, which would also include, looking at other architectures for better integration of the masker and predictor. We've also worked a little bit with end-to-end training of the model. So that's judging or getting the loss of the model on the 22nd prediction immediately rather than just the next image. And we also want to investigate incorporating some physics information directly into the model using some flow estimation techniques.
Thank you.
Thank you.
Okay, wow. Okay, I really like the slides. It's very pretty. It's very clear, and also, okay, despite the prettiness and the dark background, it's very clear, the communication. So I have to actually say that in advance, right? It's really like, okay, good job.
Thank you.
Yeah, good job. I have a question though. I'm a little confused about exactly what the output of the first network is.
Right. Yeah. Sorry. So we actually the masker is just converting all the images that come in. So here we've got the 11 images. It's just converting all those into masks. So we've trained the masker on the trained data, the label data, to generate the masks. And then once we have all these, or sets of 11 masks for each video, we just feed that into the predictor so that it can predict the next image 11 times until reaching the 22nd one.
Okay, and the masker is frame by frame, right?
Yes.
Okay, so I don't understand. Like presumably the predictor is bigger now because its input window takes 11 masks. Oh, but the masker also takes the 11 images.
Yeah.
Okay. So what's the point?
Sorry.
Okay, so the masker is a single network that takes 11 images and produces 11 masks? Or is it 11 identical networks that produce individual masks from individual frames?
So it's the masker is one network, just basically running on a loop, generating each mask for each of the 11 images.
On a loop?
Yeah, or not exactly on a loop, but yeah, it's a single network. It's not a single mask for each frame. Or
okay.
Mask.
So every pixel of every output mask is influenced by every pixel of every input image.
Yes.
Okay, I see.
Yeah. So it really could just be, or the masker would work just as well on one image input.
Frame by frame.
One image.
Yeah. Okay.
As it would with 11. That was just something we altered in our forward function.
Okay. Well, you get a little bit of consistency, right? By taking all 11 frames and producing 11 masks simultaneously, you get, you might get some error correction because there is some consistency that has to exist between successive masks.
Mm-hmm.
So maybe that's better. Okay, and then the predictor is autoregressive, right? So, I mean, the diagram you showed afterwards, that's autoregressive prediction.
Yeah, or so it's basically we're putting in the prediction into the window of right into this 11 frame input, right. And we're dropping the first mask of the last input, if that makes sense.
Right. So that's called autoregressive prediction, right? When you use your own prediction and you shift it into the input, that's called autoregressive.
Okay.
The label at the bottom is wrong, right? It starts at 13, it should be starting at 11, no?
Yeah, we just figured we were hoping no one would catch that, just because we figured
no problem.
Just color consistency and everything.
Just one picking up these things, Yann. How come you picked up this stuff?
All right. Okay, I get it. Good job.
One thing, did you backward all the gradient? So, or you only backward the 22nd?
So we actually trained the model just on, so we basically split it up into, so for each video of 22 images, we split it up into 11 different examples to train on. And
okay.
Yeah. But then that's actually what I was talking about towards the end with end-to-end training. We could actually just train the model, have it predict the next, or just the 22nd image immediately through that regressive training process, and then calculate the loss from that.
So when you train, it's not auto-regressive. It's when you do the inference, it's auto-regressive.
Yes. Yeah.
Okay.
So we're actually training it on a subtask, of just predicting the next image. And another way we could go in the future, if we were to continue this, was to predict it on the actual task, which would hopefully lead to better accuracy, which is the 22nd image instead of the n+1 image.
Mm-hmm.
Okay, so this type of autoregressive prediction is actually a particular type of recurrent net. And there is an issue with so the particular way that you're training it is called teacher forcing, which means you're not training the system to predict the end result. You're just training it to produce the correct answer at every time step.
Mm-hmm.
Okay, if I understood you properly.
Forcing,
if you wanted to train the system all the way through, you would have a problem. And the problem is that to produce a valid mask, you need to basically binarize your outputs, right? Because you're going to get logits, and then you have to turn them into binary labels, right? Or however many labels you have in your mask, and you can't backpropagate gradient through that. So you would have to train with the non-binarized masks, which may or may not be the right thing. This is actually, the reason I'm mentioning this is that this is a problem that LLMs are facing at the moment. They are trained to just predict the next word, and then they're used to generate in an autoregressive manner. But there is no backpropagation through time through the generation. It's just using teacher forcing like you're doing, and that actually is one of the problems with those autoregressive models.
Okay.
So, yeah. But that
we would have loved to experiment a little more, but just with issues or because we tried a lot of models at first, and then a lot of architectures, and then just HPC was a whole mess on its own. But I've noted everything down. So.
Okay. I have another question. Is when you train the masker, you only use the label set, right?
Yeah, exactly.
Then when you train the predictor, do you use on label set or you only use the label set?
So the first run, I think when we did our practice submission, it was only using the label data. So that was just, the 1,000 videos. And then we used our masker to generate masks for each of the unlabeled images in the unlabeled data set. And then we combined the train data and the unlabeled data to form this mega train data.
Yeah. So you also have a pseudo labeling, basically.
Sorry?
You also have a pseudo labeling.
Yes. Yeah.
Yeah. Okay. I see. Thanks. Question in the chat?
He just answered the question.
Oh, okay. Yeah. I have the same question. So.
More questions before we move forward?
Oh, okay. Okay. My laptop gonna die, so we're gonna need to charge. I'm gonna play the next video and again.
Connect the power, the outlet.
Yeah.
Right. So thank you so much.
We're team 13.
Sorry.
Okay. Well, thank you for the feedback.
Sure. Anytime.